So welcome to our fourth PSYCHE workshop on Fischer-Tropsch synthesis. Today we will have 4 lectures by 2 invited speakers and 3 project partners, followed by a discussion and a brainstorm session. Before we start, I would like to stress some points of attention for the workshop. Please all, this is for the people in the room, turn off your cell phones, and for the people online, put your microphone on mute so we have no background noise. If you have a question or point of discussion for the people participating online, please use the chat function to bring it up. And we will combine all questions. Small questions can be covered after each presentation, and bigger questions and points of discussion can be addressed during the brainstorm session. Thank you all for taking this into account, and please enjoy the workshop. Our first speaker today should have been Professor Ken van Veen from Ghent University, but unfortunately he had to excuse himself, so I will give you an introduction to the PSYCHE workshop. So the PSYCHE project is all about plastics, and as you can see, the global plastics production has stopped to increase in 2020, and also the European plastics production continues to decline. Recycling is high on the European agenda. In the circular economy, plastics production is followed by product manufacturing and use, and then there are different options after use, being energy recovery, chemical recycling, and mechanical recycling. Applying such a circular approach has a positive influence on our CO2 impact and on the feedstock use. And also the energy aspect is central to this whole approach. If we look at the plastic waste recycling, we see that we still have a gradual increase to date, and that it already largely surpassed landfill as a waste treatment option. Energy recovery still carries the highest values, but contrary to recycling, the values here are stabilizing. Which is a good thing since energy recovery still results in substantial CO2 emissions. With the PSYCHE project, the objective is also to increase the recycling numbers and to limit the energy recovery. To give you some numbers, we here have some end-of-life emissions. Incineration gives substantial emissions of CO2, and also a significant fraction of the emissions occur at the plant itself in the production step, with the conversion of naphtha to monomers. For example, options like using renewable energy and using steam cracking furnaces are being pursued, not specifically in this project, but also in other related projects of the PSYCHE partners. But as you see, if you can avoid combustion, you can already drastically reduce the carbon footprint related to polyethylene. This brings us to the PSYCHE project itself, which focuses on the conversion of plastic waste to base chemicals via gasification and subsequent Fischer-Tropsch synthesis. Ghent University is the coordinator of the project, with involvement of Professors Ken van Veen, Joris Stiebaerts, and Steven de Lister. The other partners are UCL with Professor Nicolai de Wilde, CERTECH with Benoît Cartheuser, Dominique Lalande, and Laurent Wilteris, and ENSCL and CNRS from Lille with Professors André Korakov, Mira Virginie, and Robert Fischer. The project is funded by the Interreg France-Wallonie-Vlaanderen program, which amounts to 2.6 million euros of funding. The central experimental part of the project consists of 2 parts, being the pretreatment and the gasification of the plastic waste on the one hand, and the syngas purification and subsequent Fischer-Tropsch synthesis on the other hand. So the focus here as end product is really on olefins. Besides project management, communication and education are of course also important parts of our project. Here we have the value chain of the PSYCHE project in a nutshell. We start from unsorted plastic waste, for which we look at different pretreatment methods. After pretreatment, we can go to gasification, for which we use vortex reactor technology. After that, we go to the purification of the produced syngas, followed by Fischer-Tropsch synthesis. We just want to produce useful base chemicals, mainly olefins, for the chemical industry. From right to left, we just have the plastic waste. After pretreatment and gasification, this gives us syngas, which is a mixture of hydrogen and CO. The syngas needs some purification before it can be subjected to Fischer-Tropsch synthesis, because some impurities are still present from the plastic-based feedstock. With the Fischer-Tropsch synthesis, the syngas is then converted into the desired base chemicals, such as, for example, 1,1. The first step is the pretreatment part. Here, additives improve the physical chemical properties of plastics, and a whole range of additives is currently being used. However, they render recycling much more difficult, since during the processing, they lead to vibration, emissions, leaching, degradation, and release. So it's quite important to have good ways to get rid of them before the actual recycling. Within the project, we have to be selective on the pretreatment steps on which we focus. And within the PSYCHE project, the group of Steven and Meester focuses on solvent-based techniques, for which we look at conventional methods, pressure-assisted methods, and dissolution precipitation methods. Within the project, a review paper has been written on solvent-based extraction techniques for the extraction of various additives. The objective of this first part is to realize the physical-chemical pretreatment of plastic waste via various extraction methods. An assessment is made of various extraction methods and removal of different types of additives from plastic waste, and the pretreatment conditions are optimized for a broad range of plastics. And then we go to the gasification part. The gasification is performed in the vortex reactor, which is a bit a special kind of reactor. It is sort of a fluidized bed reactor, but not as a classical fluidized bed reactor. With the classical fluidized bed reactor, you have rather low gas velocity, since you have to work against gravity, and you have a diluted bed. As the gas solid vortex reactor works a bit like a washing machine or a dryer, in which the particles rotate at very high velocity. Because of this, you can have very high gas velocities and a high gas solid state velocity. This results sometimes even in a packed bed with very short gas space times, which helps to reduce secondary reactions substantially. You therefore end up with an intensified process and overall smaller reactor. And here we have an overview of the different reactor technologies which are currently available at the LCT at Ghent University. And on the bottom, we see the different parts of the reactive vortex reactor, which is shown there on the right. The process in the vortex reactor starts with solid plastics, which go to the reactor environment via an extruder, resulting in the plastic melting. The resulting liquid is then fed to the reactor, where pyrolysis and gasification are going on. And you then end up with char, some remaining tar, but also some vaporized and cracked gaseous products that in the end are mostly CO and hydrogen. And by a simple separation, you are able to remove the char in the cyclone, resulting in syngas for the Fischer-Tropsch. The objective of this part is to perform the numerical and experimental investigation of the plastic waste gasification process in the gas solid vortex reactor. And we try to do this with the help of computational fluid dynamics. One of the aims in the project is the design of the vortex reactor to make it more suitable for gasification. And finally, we have the olefin production step. This step can be performed randomly by testing a huge number of catalysts and screen them to find the best design. In the PSYCHE project, however, we try to use mono-guided catalyst design, which means that we try to gain insight in the chemistry of the Fischer-Tropsch step. We try to relate it back to catalyst properties, and when we understand how these catalyst properties affect the final selectivities, we can use that in our models and to their scale. Looking a bit closer, we have reactor model equations. In those reactor models, we basically have a detailed chemistry, which is shown here as a microkinetics, and that accounts even for things happening on the pellet scale. By integrating all these phenomena on the full reactor scale, we basically can predict in advance what will be coming out of the Fischer-Tropsch reactor. And then we can optimize the whole system and come up with the best catalyst. It is a challenge to account for all these catalyst descriptors into the model, and thanks to the group in the field, we have various data to validate the system. Now we have models that are able to predict the experimental data, but we also need to be predictive, which means that we need to be able to account for changes to the catalyst. And this is still the step we have to take. So here we would like to acknowledge impact for the funding of the project. Our project received also co-financing from the provinces of East and West-Flanders and from the Walloon Region. Are there any questions related to the PSYCHE project itself? No, then I would like to give the word now to our second speaker today. Our second speaker today is Professor Evgeny Kondratenko from the Leibniz Institute for Catalysis. After graduating from the Novosibirsk State University in 1991 and a PhD at the Siberian branch of the Russian Academy of Science in 1994, he performed a habilitation thesis at the Technical University of Berlin in 2007. In 2009, he became senior lecturer at the University of Rostock, where he is professor since 2020. And since 2019, he is also speaker of the topic field Kinetics, Theory and Mechanisms at the Leibniz Institute for Catalysis. He already received several awards, such as the recognized reviewer for catalysis science technology in 2020 and the diploma of highly active and competent reviewer of Chimie in 2024. So again,
thank you very much. First of all, I would like to thank Elizabeth and Andrei for inviting me to be here and to share with you our recent results on this topic. Before I will go to the main topic, I would like to give a brief overview of what we do in the field of CO2 related conversions. Typically, we are interested in CO2 conversion with methane to syngas, so-called dry reforming of methane. A few years ago, we introduced a process for production of propanol from ethylene CO2 and hydrogen. CVD to propanol is around 100% based on CO2. We have started very recently CO2 to methanol, and today I will talk about CO2 conversion to higher hydrocarbon. What is our mission? We want to understand how reaction proceeds on a level as elementary as possible, and we want to determine active site, active phase, active species, and then we try to relate this kinetic or mechanistic information with a kind of active sites to get fundamentals for tailored catalyst design. Typically, this approach is applied for different reactions, not only for this CO2-related conversions. How can we achieve our purpose? We follow this approach. I divide it into 4 pillars. One pillar is we try to prepare catalysts as defined as possible. In case of today's talk, I will talk about iron-based catalysts, and our purpose was to prepare, let's say, single phases of alpha iron oxide, gamma, or the mixtures, or we also can prepare differently structured iron carbon oxide species, or a kind of oxide carbides, or we can also prepare supported catalysts with well-defined iron species. And what we also have done, we used so-called big data analysis to extract information from literature data, which can be useful for catalyst development. After we have such catalyst, clearly you need equipment to test it, and in our lab we use so-called high throughput tests. In one such reactor, as shown here, we have up to 50 fixed bed reactors operated in parallel. It can operate up to 20 bar and up to 600 degrees C. To get some deep mechanistic insights, we use transient techniques or operand the catalyst characterization. Here's a photo of so-called TAP reactor, temporal analysis of process reactor, and what we also try to do to improve selectivity, we try to combine different reactions. As for example, shown here, you can combine reverse water gas shift reaction with COX Fischer-Tropsch. You have such a reactor, but 2 reactors are in series. Now I will start with presentation of results. At first, we can overview what we have done with machine learning. We have collected a lot of data, around 400 data points from literature data point 400 catalytic data, not data points. We have catalyst composition, physical chemical properties, some phase composition, and so on, how catalysts were prepared from which precursors, many data, also data about the performance, which activity, selectivity, and so on. And we try to analyze this data to identify descriptors which are relevant for catalyst preparation. And what we found here, just I did not go in details how we did it, what we found for the most important descriptors for the rate of CO2 conversion are shown here: total pressure, catalyst pretreatment, and presence of potassium promoter. To increase selectivity to C2 plus, it means no methane, just methane and higher. It is useful to use bulk catalyst and, if possible, promote catalyst. And what we also found that promoter electronegativity should play a role. This is such simply theoretical prediction, and I will show later that we have proved it. Yeah? And to increase olefin to paraffin ratio, we should use also bulk catalytic promoter. And today I will not go in details in many topics, just to start with bulk catalyst, and we decided to exclude any promoter. Promoters can make troubles. People know that if you have promoter, you can increase performance, but it is difficult to decide which role does promoter make. And at first we simply decided to use non-promoted catalyst just to show how spatial distribution is important. What we have done, we have prepared, here's missing something, okay, strange, here you don't see colors, yeah, me too. We have prepared catalysts which have different compositions. They have iron carbide, oxide, and so on, and then we have tested them in the CO2 Fischer-Tropsch, and we found that for some catalysts, you see, this one didn't have Fe5C2 initially, but after reduction, after catalyst, it has a lot of carbide in the first segment, but in the big segment, no carbide. Here you have carbide in the beginning, and you have in the smaller and larger. Here, if you will try to find a correlation between the concentration of iron carbides and performance, it is difficult. What we have done, we have decided to determine catalyst layer which is required to achieve a certain degree of CO2 conversion. In this layer, we have determined catalyst composition in spent material. And if you do like this, you can find that selectivity to C2 plus really increases with the concentration of iron carbides, and methane selectivity increases with the concentration of metallic iron. It means to suppress methanation, you have to avoid the presence of iron carbide. And we went further, we simply prepared a family of catalysts, again, Fe2O3, we used iron oxalate and decomposed in a certain way to get alpha iron oxide with different sizes of crystallites, or mixed alpha gamma oxide with different content of alpha. And we simply, again, use this materials for catalytic test. What we found when we compare with the state of the art, what people have reported. All these great data points are from literature. And the data contains also materials with promoted iron oxide, even including alkaline metals. What you can see that our unpromoted catalysts, they can have selectivity to C2 plus above 80%, to methane below 10%. And we have again two groups of materials, blue and red one. They're prepared from different iron oxide. But why do they perform differently? We wanted to answer this question, and what we have done at first, we have performed very simple so-called selectivity conversion relationship to know how products are formed from CO2. Here, I show you how selectivity to CO, methane, and C2 plus change the CO2 conversion on this catalyst. You see that CO selectivity drops. It means that CO is further converted to other products, and the products are methane and C2 plus. When we use this data, we can obtain this reaction scheme. CO2 gives in parallel CO and methane, and CO can also give methane, and CO gives CO+. When you extrapolate this the data point to the conversion of CO2 zero, this intersection gives you information about this pathway. The slope of this dependence gives you information about this pathway. When we use this information, and this scheme is valid for all catalysts tests. And when we now try to compare, let's say, hydrogenation ability of catalyst of CO2 to methane, depending on reducibility of iron oxide. Here is the temperature of maximal rate of reduction Fe2O3 to Fe3O4. You see that the higher the temperature, the higher the ability to convert CO2 to methane. When we compare it with CO hydrogenation to methane, here we see a less pronounced dependence. Okay, it means somehow reducibility again affects the property of iron carbides to make methane from CO2 and to make methane from CO2. The question is again why? What we have done, we determined spatial distribution of iron carbides and iron oxide in catalyst layer. Here on this plots, you see how iron carbides and iron oxide are distributed in the catalyst layer. And here in these data points, we measured so-called segmental reaction rates in each segment. What you see, these materials, these two, they contain in the beginning very low amount of iron carbide. But compared to this one, they're highly active. They produce a lot of methane and produce a lot of C2+. It's high activity, but they do not have a lot of carbide. And then clear the rate of C2+ methane decreases because of integral reactor operation. But when you look this black data point, that is the ratio of C2 to methane, you see this ratio for this together simply decreases. It means both rates, methane and C2+, decrease in a similar way. But in the case of this materials, we have a maximum and even much higher ratio. It means the carbides which are formed here, they're intrinsically less active, but they are highly selected to C2+, not to methane. The question is why? Again, we try to determine some property, and what we found, if we use Mersbauer spiroscopy, and from Mersbauer spiroscopy, we determine the ratio of carbon to iron and iron carbon. And we call this ratio as defectiveness of iron carbon. Typically, if you have an ideal iron carbide, the ratio should be 0.6. And what we found that if the ratio decreases or increases, the rate of methane formation decreases. It means when we go from defective to less defective iron carbide, the ability for methanation decreases. Actually, what we have found with another catalyst. And what is important here is the ratio of C2+ to methane. If we decrease defectiveness, we suppress methanation, but in favor of C2+ formation. You see, just by tuning the property or the defectiveness of iron carbide without having any promoter, you can control selectivity to C2+ of methane. And in the last part of my talk, we decided to use promoters. How promoters actually work in this reaction. And what we have done, we simply prepared iron oxide with different alkali metals. Lithium, sodium, potassium, rubidium, cesium, and we use this number tells you the ratio of alkali metal to iron. This is very low number. We decided to use very low to minimize any possible effect of the promoter on, let's say, activity to react with CO2 with CO also. What we typically have done again selectivity conversion relationships. What we found that for all catalysts, it doesn't matter do we have or not have promoter, CO selectivity decreases with rising CO2 conversion. It means CO is a primary product. It is nothing surprisingly. And this product is further hydrogenated to what? To surprisingly not to methane, you see methane selectivity does not change practically with CO2 conversion. It runs parallel. It means that methane on promoted catalyst simply forms through direct hydrogenation of CO2. And by alkyl metal promoter, we suppress this undesired pathway. And what is formed from CO, CO2 plus. CO2 plus hydrocarbons are formed from CO exclusively. Methane is not formed on promoted catalyst. Means we can come to this reaction scheme. CO2 gives into parallel CO and methane, and then CO gives CO2 plus hydrocarbon. And what we know is the kind of alkyl metal promoter affects this pathway. Interesting. If you have lithium, it doesn't have a big positive effect. Yeah? And only if you have, let's say, sodium, potassium, rubidium, cesium, the effect becomes much stronger. The question is why? Again, as I thought in our research, we are interested to understand why. We are not so much interested in catalyst development, but we want it first to learn why, and then we can try to develop a catalyst. And what we have done, we had a simple idea. All these products are formed from CO2, CO, and we need hydrogen. And we thought might be the promoter effect simply catalyst ability to activate hydrogen, CO, and CO2. Okay, and what we have done first, we simply investigated activation of hydrogen by HD exchange test. We use PEN catalyst, and what we found that here I show so-called relative rate of H2 activation, and here I plotted electronegativity of alkali metals, and here I plot the rate. You see that if electronegativity changes, decrease of the promoter, the rate decreases. What we also have done, we investigated how CO2 is activated from a mechanistic point of view. And we found that this reaction scheme can describe activation of CO2. We were able to determine this kinetic parameters for all catalysts, for spent catalysts. Yeah? And here I show you how the difference in the electronegativity between iron and alkyl metal promote affects this constant. You see that the absorption constant and dissociation constant increase and desorption decrease with this difference. Okay, we know that electronegativity affects hydrogen activation and affects CO2 activation. What's about CO? For CO, we found that the same scheme as for CO2 can describe CO activation, and also we found here that electronegativity plays a role, but a different role compared to CO2. Now, what we know that electronegativity is important for activation of hydrogen, CO, and CO2. But how is this relevant for catalytic data? What we have done, simply, if we want to increase overall rate of CO2 conversion, in terms of CO and CO2 activation, this ratio is highly important. If you have a strongly absorbed CO2, the rate of this constant I showed you in the previous slide, we determined that. Then we see that if CO2 is strongly absorbed, you will get CO2 rate conversion low. For H2 activation, the higher the catalyst ability for H2 activation, the higher the rate of CO2 conversion. Logic, yeah? In terms of methane formation, you see the rate of methane formation depends on catalyst ability to activate CO2. I showed you, in this case, CO2 is formed, well, methane is mainly formed from CO2. Again, here CO2 plays a role. To suppress methanation, you have to decrease catalyst ability for hydrogen activation. Logic. To form hydrocarbons, you need less hydrogen compared to methane. Methane needs high amount of hydrogen. C2 plus less. And then if the catalyst is not able to provide as high as possible concentration of hydrogen species, you will get C2 plus. And in terms of C2 plus formation, what we need the catalyst ability for CO absorption and also for hydrogen activation. Now we have these fundamentals which can be used theoretically to tune further catalytic performance. Okay, after this, I would like to summarize that I hope I convince you that simple reducibility of iron oxide can be used as a descriptor for tuning performance of catalysts in terms of selectivity to C2 plus hydrocarbons in CO2 hydrogenation. For unpromoted catalysts, the concentration of iron carbide is important, but also is important the ability of carbide to activate hydrogen in CO2. This property can be tuned by alkali metal promoters, which affect actually electronic properties of iron in iron carbide. Okay, and I would like to thank you for your kind attention and acknowledge people who work in CO2 team and people with whom I collaborate, and this is people who gave us money. What was important to do this research. Okay, thank you.
Thank you, Professor Kondratenko. Are there any questions, both in the room or via the chat? Andre, I will give you the microphone for the room.
Yeah, hello. Thank you for interesting talk. I just was wondering, you talk a lot about the C2 plus selectivity. What are the main compounds in the C2 plus group that you get with these catalyst systems?
Typically, we have a so-called Schutz fluoride distribution. The main, let's say, C2 plus is then decreases. It's more or less very similar to classical CO.
Okay. Yeah. Thank you.
Yeah, okay. Thank you.
Thank you for interesting presentation. I have the question about the reaction mechanism with the promoted systems. You told that in this case, CO2 is directly converted to methane and CO is converted only to C2 plus. But in this case, you have no Anderson-Schulz fluoride distribution in case of CO hydrogenation, because according to these kinetics, you always have CH4 production, methane production, and how it's possible that CO is directly converted only to C2 plus.
Okay, I understand what you mean. We cannot completely exclude that CO is also fluid to methane, but to much less extent compared to CO2 methanation. It can be, but from our selectivity conversion plot, actually, this data, they can be interpreted like this. CO2 gives a top CO, and CO doesn't dissolve but hydrogenated to, let's say, methane in CO2, but it will be the same. I mean, the dependence of methane selectivity on CO2 conversion would be the same if we assume that CO2 can absorb, gave a top CO, this top CO doesn't dissolve, but simply shows so you see the same dependence. This is unfortunately limitation of such approach.
And thank you. And the second question is about the defectiveness of iron carbide. So in your case, as I understood, the most effective catalyst will be monocrystal of iron carbide, or not?
Okay. I don't want to tell about monocrystal.
Because it's maybe a balance between the defectiveness and surface area.
This is what we obtained from two independent studies. Carbides which are less defective, they also less active, but they are more selective in terms of C2 plus hydrocarbon formation. Somehow, good. If you assume that defect sites are required to activate hydrogen, I mean, it is more or less generally said, then the higher the defectiveness, the higher the ability to provide hydrogen species, and the higher the possibility to form methane. And but when you make less defective carbide, you will generate less hydrogen active species, and then you will suppress methane. This is our assumption.
Thank you.
Okay, thank you for a very nice presentation, interesting work. So it was nice to see how in the phased bed reactors you are using, there is a profiling composition of the catalyst. So is this inherent then to the evolution in the gas phase concentrations of the reactants? Or is it also a matter of operating conditions, and could you tune the behavior by moving to other conditions?
This is a very good question. This is, I mean, the profiles what we have, they are due to water. Water simply oxidizes iron carbides, yeah? But what we know is that some carbides, they do not want to be oxidized by water, and some like it. We still do not know how to tune this property, but this is an assumption that water one time, and another point, CO. To form carbides, you need CO, and along catalyst bed, CO partial pressure decreases, huh? And water increases, and you have such a situation, which is, I mean, here you have to define to develop carbides which can be formed even at low partial pressure, so but they should not be oxidized by water. And what we now try to synthesize only carbides and then test them against water and to see how they can oxidize by water, to learn which property of iron carbide is important to suppress the oxidation.
Yeah, and would it then make sense to do the investigations in a mixed flow reactor in a CSTR? Such that you can.
This would be an interesting, yes.
Such that you have a point composition,
yes,
and
you're
then
right.
At least the catalyst should be uniform.
Yes, you're right. This is, it would be very nice to use a kind of fluid-based reactor where we should have more or less same catalyst composition. You're right. Yeah. But we don't have this option.
Well, yeah. Okay, well, but we could see there. We do have such type of reactors, so
nice,
that might be a lead. And then the second question was well related to the reducibility. When we do our modeling of Fischer-Tropsch synthesis, we use as catalyst descriptors atomic chemisorption enthalpies of hydrogen, oxygen, and carbon. Of course, I would say that's modeling really of the reaction from the mathematical point of view. So you nicely start more from the observations. Do you think there would be a direct relationship between reducibility and the atomic chemisorption enthalpy of hydrogen, for example, or well, would it still be more complex than that?
It can be, yeah. Now you are absolutely right. We try to collect now as much as possible data, and then to relate this data to, let's say, to chemisorption activity like this. This is, I mean, this is very important point. I think, yes.
Yeah. Okay. Thank you.
And our third speaker today is Jean-Paul Lange from Shell. Jean-Paul Lange is Senior Principal Science Expert at Shell Projects and Technology in Amsterdam, where he has been exploring novel catalytic processes for producing fuels and chemicals from natural gas and oil, and since more than 20 years also from biomass and plastic waste. His research embraces heterogeneous catalysis, chemical engineering, conceptual process design, manufacturing economics, and technology strategy. Before joining Shell, he was postdoctoral fellow at the Lehigh University in Bethlehem in the US, got his PhD at the Fritz Haber Institute of the Max Planck Society in Berlin, and graduated at University of Namur. Jean-Paul Lange is also professor in chemical biorefining at University of Twente, where he is investigating thermochemical and catalytic routes to convert biomass to fuels and chemicals and to recycle plastic waste.
Morning, everyone. And let me first apologize not to be among you for this very interesting discussion on the role of syngas for fuel and for chemicals in the future. The organizer invited me to discuss a bit the broader picture of circularity and of alternative carbons for the chemical industry, and it is what I will try to do in the coming half an hour. You will see eventually more details of the lecture in the 2 papers cited here, and you will find the citation back in the conclusion slides in the case you didn't have the time to write it down. Now, I'm forced to show you this cautionary note, which is a very wordy way of Shell lawyers to inform you that Shell declines any responsibility for financial transactions that you may do based on the information I'm sharing with you. So if you after the conference you rush into your bank and you make a fortune, that's your own fault. It's not Shell's fault. But this being said, let's look into the plastic recycling and eventually what syngas can play with it. And I'll try to do that in the 3 major chapters: the why, the how, and the when. On the why, maybe just sketching rapidly what is the chemical industry, how I do see it here. And it is about making plastic. About 90% of the chemical output is going into plastic, mainly from let's say from hydrocarbon plastic, polyolefins, polystyrene, rubbers, and the like, but also significant fraction, though smaller, significant fraction of a functional polymer, engineering plastic containing oxygen, chlorine, or nitrogen into the building block, into the monomer. And of course, as you know, all those plastics are coming from a couple of main building blocks, olefin and aromatics. But because the output is about plastic, we need to understand where this plastic is going to. About 40% going into packaging, being films, being rigids, polyethylene, polypropylene, as well as PET. And you'll have a smaller fraction going into construction for piping, for instance, for windows and doors, for insulation. And then you will have a plethora of other applications, all much smaller, being automotive, electronics, and many, many others. And those are the kind of sectors that the plastic industry is serving, eventually being pervasive throughout the whole society and the whole economy. Now, you are fully aware of the energy transition, and I will not insult you in telling you why we have the energy transition, and tell you about climate change and the like, but I would like to focus here on the impact of that transition that it has on the chemical industry. Because when we talk energy transition, we typically talk about energy and not the chemicals. But the chemicals and energy sector being highly connected, highly related, it will have impact onto the chemical business. And you see here on the screen 3 major challenges that the whole industry is facing. And I will focus on the last one here about circularity. But I can't do that without addressing shortly, just with this slide, shortly the other 2. The first one is about the hydrocarbon diet, realizing that the energy is withdrawing from fossil hydrocarbon. We want to move to wind energy, solar energy, maybe to hydroelectric. And you see particularly the transportation sector getting out of the fossil hydrocarbon. That will have a major impact onto the chemical industry because this is the main feedstock for the industry. From one sense, it is a good stuff that the energy is retracting because we have much more hydrocarbon to convert to the chemicals. But from the other side, it is a bad thing because it also means that the chemical industry will have to pay for the whole value chain, eventually up to drilling the ground to get the oil. And that means that the feedstock will become much more expensive in the future. So energy transition will have an impact on the cost and the availability of our feedstock. But it also has an impact on the way we are running our industry because of the CO2 emission, because of the climate change. The whole society is bound to go net zero by 2050. And so does the chemical industry, which means that we need to switch the whole industry into alternative, into renewable and green, carbon-free energy. And it is a hell of a work to do so. Just to take as an example, if we decide to convert a steam cracker into a PV cracker with solar energy, we will need, the steam cracker will typically need about a gigawatt of power, and it will need it 24/7, 52, continuous, no interruption. We can't turn the cracker down because we have a cloud passing by or because it's night. So that will have dramatic impact because of the volume, because of the security that we need to have for operation. So the whole CO2 is another major challenge. But the last one, that will be the focus of today's talk, is about the plastic litter. Plastic litter that is eventually growing for many decades, but eventually hit the news in 2017 with really, let's say, astonishing pictures of plastic swimming in the oceans, plastic being everywhere. And that could mean that society as a whole will reject plastic, which is a very bad, will be a very bad solution, because plastic is providing very valuable service to society. And it's not the plastic we need to reject, it is the litter that we need to reject. So what are the options that we have? If we don't want to reject it, we'll first have to recycle it significantly, and we will talk about recycling a bit more. Recycling will have another impact. Not only we will not have litter, but the waste that is not going into litter is a waste that's typically incinerated and going into CO2. We will not have that CO2 as well. So recycling is eventually contributing to that solution over here. And it is also contributing to that solution over here, because now that we have more recycled plastic coming into the plant, we need less virgin hydrocarbon and less fossil feedstock. So you see that recycling plastic becomes eventually a centerpiece in the solution of the industry. But it's not all, because you can't dream of closing that cycle for 100%. You will always have losses all over the place, and you will need to offset those losses by fresh input of carbon into the cycle. And if this can't be fossil, then it will need to be renewable, being CO2 or being biomass. Those will be topics that we'll need to address, but today I will mainly focus on the circularity here. So that is about the why and the major challenge industry is facing, and the central importance of recycling without that solving those challenges. Now let's look a bit on the how. How can we do the recycling? We know the linear economy where oil is converted to product, and the product can't go to litter. The product can't go to energy either, because it will become a CO2 intensive source of energy. So we will need to recycle, and we have a couple of options for recycling. Maybe the smaller loop here, the mechanical recycling, you just wash, remelt it and make a new object. Or you can depolymerize it back to the monomer and repolymerize it again. Or you go even to the pyrolysis, you make a hydrocarbon, a much bigger loop. And then you go through the whole value chain. And you can go even one loop further that is not on this graph, but that is the central piece of your conference today. It is about gasification and having everything converted to syngas, which is a precursor to a hydrocarbon. It is not a feedstock, it is a precursor to a feedstock, because from the syngas, you need to go back and make your feedstock, being methanol or being Fischer-Tropsch. So you have a couple of options, and you may wonder, what are the options that you need to apply? When do you apply what for which kind of plastic? And the first rule of thumb will be, let's take the shortest loop as possible, the smallest loop as possible. And why you need the smallest loop is because by making a small loop, you avoid all the waste that you are otherwise producing upstream. You avoid all the energy emission, the consumption that you have for making that feedstock, or the waste, the chemical waste, inorganic waste that you are producing together with your product. So the shortest loop should have your priority if you can do that. And if you can't, then you need to move to increasingly bigger loops. But before you start with the shorter loop, you have to sort the plastic. We have a number of technologies being commercially applied today, and a few others under development. And typically start by collecting the whole post-consumer waste, and I'm talking here about the mixed one, the post-consumer waste. Collecting all the post-consumer waste, removing the metals and the ceramics and the textile and the cardboard and what have you, ending up with a plastic-rich waste. From there, you will blow off the films for dedicated recycling, and then you will try to disperse your waste onto a conveyor belt and have near-infrared detectors looking at your plastics and try to identify which plastic it is. And once you recognize the good plastic, you blow it away into specific bins, and otherwise, all those that are not what you're looking for will be collected into a special bin or into the next conveyor belt to sort the next plastic. And in doing so, you can sort quite a number of plastics, but you still end up with a waste stream, which is those components that you can't really assign to or that do not have the quality that you need for the given plastic. That is what is done today, but there are much more technologies being developed and being demonstrated. The one here, number 3, is hyperspectral imaging, which is about the same as what we do here, but not on one spot. You try to image the whole object to make sure that your object is pure, the whole bottle, the whole tray, for instance. But otherwise, you can put fluorescent pigment to mark your plastics. You can do watermarks, which resemble a bit of a QR codes to understand exactly, to identify exactly what is the plastic, its composition, its origin, etc. You can combine them all with artificial intelligence and a few other techniques that allows you to refine and refine your sorting and make it even more powerful than it is today. So there will be quite a lot of development there to have a good quality stream. And once you have a good quality stream, of course, you go for the shortest loop, you go for the mechanical recycling. And you go for that one because of efficiency, material efficiency, you have the highest yield in recovery, and also the lowest energy demand, the highest efficiency in your energy. But you also have some limits that you will hit pretty rapidly. Limit on the polymer quality. If you look at the polymer, you will not have a single grade of polymer. If you look at the polyethylene, you may have hundreds of grades of polyethylene, and you will have the market average of those 100 grades. So you will not be able to make very specific applications that need a specific grade. Moreover, your polyolefin, your polymer chain will probably be degraded, oxidized, maybe cross-linked, or maybe broken down a little bit, be damaged by the use, by the processing, the use, the UV, and the heat, etc. So you will not get exactly the same quality of the polymer. But you will also have a number of contaminants in the polymer. Polymer are rarely a pure component, but they will have additives, they will have fillers that are put intentionally within the polymer to protect it or to improve its properties. You will have the average of all those contaminants, those additives into your polymer. And the sorting is not perfect, so you will have contaminants from the sorting. You may have also contaminant coming from the waste in form of dirt and other components, etc. And all those will impact the quality of your polymer, which will partly be critical if you decide to go for food contacting application for food packaging, and you don't want all those contaminants, for example, to contaminate your food. And there are options to remove those contaminants by extracting the contaminant or by dissolving the polymer and reprecipitating it, but then it starts to be more complicated and more expensive. But there are also options being developed over there. So for the mechanical recycling, that is the beauty, but also the limits. So if you hit some of those limits, what can you do? You need to go to the chemical recycling. And then you wonder, do you go back to the monomer or do you go back to general feedstock? And to understand that dilemma, let me show you this graph where you will have kind of 15 major polymers in a landscape. and a landscape that will help you a bit identifying what to do with the polymer. On the x-axis, you will have the heat of depolymerization, which is eventually a measure for how easy it will be to go back to purely your monomer. On the y-axis, you will have the total integrated waste that you are producing during making the polymer, which is a measure for how much complexity you have in making the polymer from virgin oil. And this allows you to divide your graph and your polymer, associate your polymer into two major quadrants. In this one, when you have low depolymerization energy and eventually high investment into the polymer, you want to depolymerize it, you want to recover your monomer for reuse later on. While in those small box where you see you can't really recover your monomer, but eventually your feedstock, your waste resemble a bit of hydrocarbon feedstock. You didn't invest so much chemistry and energy in making it, you could convert it back into the feedstock. And those are the two archetypes you have in advanced recycling on chemical recycling. You will see the polyolefins falling in this box. You will see all, let's say, most of the condensation polymer falling in this one, like PET or the nylon. And you see the higher you are on this blue box, the bigger the drive to recover the monomer. And this is helping you a bit to understand what you can do, how you will do that, and how you will do that for those polymers. You can depolymerize like glycolysis for the PET, but let's not dwell too much on this one. For the hydrocarbon, you can do pyrolysis and crack them back to hydrocarbon. Depending on the conditions, you can crack them back to waxes, aromatics, or even a mixture of lower olefins. And you do that by feeding here your plastic into a hot reactor, and you strip off, distill off the hydrocarbon that you need, that you want to recover for feeding eventually to a steam cracker. Those are the kind of technologies that you have at hand to do the recycling. But now the last question, and an important one, is when can we do that? How fast can we deploy those technologies? So let's first look at where we are today. And when we are today, you probably have seen similar pictures. Today, about 2/3 of the plastic is ending in landfill. A quarter is being burned in CO2, being with energy recovery, or more than often being just burned on the field to get rid of the waste and generating dioxins and fumes and smoke and what have you. And only a very small fraction, like about 10%, is being recycled mainly by mechanical recycling. And you can see that, of course, this is not the circular economy that we want to have and that we sketched in the very beginning of the lecture. So where could we be in 30 years from now? I would hope, and that is really an optimistic hope, I would hope we will go near to zero landfill and leakage. We will be able to ramp up mechanical recycling maybe to 20%, and maybe not much more because of the physical limit we have on mechanical recycling. We'll try to complement that by significant boost of chemical recycling, let's call it 30%. And we still have 50% of the carbon coming out into the atmosphere. So eventually, what we have done for a large part is shifting, while we increase this recycling, we shift quite a bit of the contamination in land and water to contamination in the air. And this scenario is optimistic because in the meantime, the demand for plastic will probably have tripled, which means that the effort we have to ramp up the recycling is 6-fold for mechanical recycling, more than 100-fold for the chemical recycling, which will be a tremendous job to get there. And in doing all that, what we will have done is not reducing the CO2 emission, but increase it by 7-fold compared to today's emission of by incineration. So you see that even that optimistic scenario is not quite where we need to get it to. And this CO2 is leading us to the question, what can we do? Can we do CCS and put all those 2 gigatons of CO2 on the ground? I think the volume is really large. And I doubt we can do that, or I doubt society will accept to solve the problem in that way. So what we'll have to do is not do CCS, but also we will not accept fossil anymore. So we'll have to recycle the equivalent of 0.7 gigaton of carbon. We have to put it back into the loop, into the industry. And that will need to be renewable carbon, either CO2 directly that we capture from the air, or it will be CO2 captured by the biomass and recycled in form of biomass. And the option to recycle that CO2 is a whole discussion in itself, and I will not have the time here to go through it. But it is important to realize we will need a lot of this renewable carbon. By 2050, it could be to 50% of the carbon, because we won't be able to close the loop. So if we zoom forward to the end of the century, how could the industry look like? And here you have a bit of a split of the various feedstock, where I would personally expect the fossil to peak around 2030 to 2040, only for making the chemicals. So it is tripling on what we used at the beginning of the century. It's only around the middle of the century that we will see the recycling becoming really significant feedstock, maybe as large as the fossil, and the renewable carbon becoming very significant somewhat later in the second half of the century. And what is the basis for this scenario? I think it's just worth spending a minute on it. The basis is fairly simple. We will, for those various technologies, try to estimate when the first plant, commercial plant, can be built and can start at industrial scale. And some has been started in the past with already mechanical recycling. Some will be way in the future if we want to capture CO2 from the atmosphere and do electrolysis of water and do that in an affordable manner. That's probably not for tomorrow. And the other ones will be somewhere in between. Once you pin down the starting of the first plant, you grow that technology at tremendous rate of 30% per year. Tremendous rate because the energy did not grow more than 20% per annum. Now we are assuming 30% per annum, driven by politics and driven by a lot of money, because that would be really expensive to accelerate in that way. So we try to push all the alternative carbon into the diet of the chemical industry, and what we can't feed with alternative carbon will still need to be the fossil. And that is why you will have a peak here around 2030. We can't ramp up all those technologies much faster than what we have. And with this, let me close this chapter on the how, let's say the why, the how, and the when, and maybe reminding us the 3 major forces that are pressing the chemical industry to change, to transform, which is the hydrocarbon diet, the climate change, CO2 emission, and the central piece here, the circularity, recycling to solve the litter, but also contribute to solving all the others as well. And that will require quite a lot of development in the form of sorting and collection, but also improving the mechanical recycling, as well as deploying seriously now the chemical recycling for the lower quality waste. But as you have seen, it will not happen tomorrow, so we still need to work for the alternative. We still need to improve our fossil technologies, because we will have those in use for kind of 30 to 50 years. So we want to make them as efficient and as low as footprint as possible. And we also know we won't be able to close fully the carbon loop in the recycling. So you will have to develop technologies to feed back renewable carbon into the loop. And with this, I thank you for your attention, and I give you back the mic, Elizabeth.
Okay, thank you, Jean-Paul. Are there any questions? Any questions in the room?
May I ask a question, Paul? That's
Yeah, sure.
yeah. Thank you for your talk. Very interesting, very enjoyable. I would like your view from the work that you've been doing and your experience looking at the advanced recycling technologies. You mentioned in your optimistic scenario something around 30%
Yeah.
derived from advanced recycling. In your view and what you've seen in your studies, what percentage would you assume would be possible from the gasification route? And
Yeah, the gasification route, the gasification route is, let's say, the most robust because you are cracking everything down to syngas. So in principle, the gasification route could be able to close quite a bit of the loop, to go very deep, but it will be really expensive. So the issue of gasification is probably not so much technology, although it will be on collection and sorting. You still need the collection and the sorting, but it will be mainly on the economics, for two reasons. Because you need a lot of you need to do a lot of chemistry in order to go back to your plastic from syngas, to make the syngas, clean the syngas, and do the synthesis thereafter. Secondly, this one is really intensive. You want to do very big scale, and you don't have a waste at that scale. Let's realize that today's pyrolysis technologies are operating somewhere between 10 and 30 kiloton per annum of reactor. A steam cracker is operating at 3 million ton feed per annum, a factor 100 or beyond that one. And if I look at the gasification plant, like Shell's Pearl technology in Qatar, which is using the easiest feedstock that we have, which is natural gas, or the cleanest feedstock, we need to operate that at 6 million ton per annum of feedstock. So even a factor 2 beyond the steam cracker. So you see that the collection of and the supply of the waste for the big scale will be a big challenge. So I think that's the challenge of gasification is economics. Am I answering your question?
Okay,
Also in the chat there are some questions. I assume there is more energy needed for pyrolysis gasification of plastic waste than the energy gained. Is microwave heating an alternative?
Yeah. For the whole pyrolysis bit, the pyrolysis is not selective enough, which means that it's produced sufficient hydrocarbon to run it. So we will have methane in the pyrolysis, we'll have char in the pyrolysis, we also have methane in the steam cracker, and we can use that in order to generate the energy that we need for running the process. So that is not a major problem, but using that, of course, will require you to emit CO2, and that will have a CO2 penalty in there. So it would be much better, of course, to develop, let's say, leaner technologies for recycling those hydrocarbon. But I don't see which one it will be, because you have very strong energy bonds, as I showed you in one of the slides, strong bond energies into the plastic, and you'll need to crack that one. And gasification is not helping you, because gasification is eventually oxidizing a part of your polymer to make your syngas, transferring all that oxygen into the hydrogen, making a lot of water, and eventually is also spending a lot of energy. So for me, gasification would be worse in terms of energy balance. And I don't know how we would crack those polyolefins better than pyrolysis. I'm open for any suggestion you might have.
Okay, thank you. I see there are are also some comments of Eric Vanquier. Would you like to comment a bit on them, please?
I would need to check the.
Yeah, but maybe it's best if Eric first gives a bit his view or on his comments.
I see a longer. Let probably switch off all the. Oh no, that's not. Oil and gas demand is put past the pandemic. No, it's up past the pandemic. Gas very much so. Oil as well. Even a starkly higher price. Society worldwide is buying more oil and gas. Definitely, we are resuming our track on consuming more oil and gas, and that is not helping the transition. So I agree, and that is a bad development. Solar wind cannot provide the continuity, indeed. They will not power the factories, indeed, unless we have a lot of storage, and the storage will be tremendous. So I also agree with that comment. Renewable energy for powering the plant will be difficult. Yes. I'm closing the loop, and that will be costly in terms of material, in terms of energy. Yes, but we can't afford to have the carbon being lost into the environment. That will mean that our product will likely be more expensive. But the plastic are damn cheap. We may have to pay more for it. We may have to pay more for energy as well in the future.
I see there's an online question. Somebody raising his hand.
Yes.
Go ahead, please.
Hello, it's Mark Howard.
Hi, Mark.
I'm just interested in your view on renewable methanol. Waste to methanol is already a reality, albeit at small scale. Methanol to olefins is a reality at very large scale. Do you see a significant role for renewable methanol in the future chemical industry?
It could well be. It could well be. My big question and worry will be back in the cost. How effective and how, let's say, cost effective can we make that renewable, that waste-based methanol? But that will eventually be the, let's say, the last solution we have to take care of the, let's say, of the crappy part of the waste. So there will be a role for it, but that will not be a cheap one.
There are two related questions in the chat. However, biocatalysis is also a potential technology to depolymerize plastics, which must be considered. And then how about the use of enzyme catalyzed recycling, the potential in the 50 or the 100 years? And after all, you said we will have to rely on CO2 recycling technologies to close the gap of carbon recycling even after 50 years. Could you elaborate more? That
Okay,
one is a bit separate.
Yeah, let's first tackle the enzyme depolymerization. Yes, enzymes are shown to depolymerize plastic, and particularly the the condensation polymers, the polyesters, for instance. But those are plastics that we have no problem to depolymerize. The problem we have is the continuous carbon-carbon chain of the polyolefins, the condensation. We can depolymerize them, and we don't need a high dilution that we have with enzyme catalysis. And we can do that at a much higher rate in better controlled environment. So I'm not so sure that enzymatic depolymerization is helping me on industrial scale. Now, and once the enzyme will be able, can also digest the polyolefin, they will not deliver me the olefin, they will deliver me different feedstock. Eventually they could, if they can digest it, they will be able to metabolize them and give me different product. It will be a very different recycling, making me different building blocks. We will see whether to which extent organisms can go there, and wondering whether this is really a solution for recycling, or is it a solution for taking rid of the waste and degrading the materials that we can't really recycle and eventually end up in landfill. Those are for the first two questions. Now, what was the last one that you mentioned?
After all, you said we will have to rely on CO2 recycling technologies to close the gap of carbon recycling even after 50 years. Could you elaborate more?
Yeah, I think we will with time we will try to narrow the gap in recycling and narrow the losses, but we will still have to put fresh carbon in there, and that will have to come from CO2. I don't know. I mean, I hope we will be able to get out of the fossil, and that we will be able to run on renewable carbon to have a really circular economy, and that for the centuries to come. And I don't see alternative carbon source than the CO2 being directly from the air or being the biomass. I will expect the biomass to be a faster solution. Biomass can be competitive today, and CO2 coming from the air is not competitive by no means, not competitive today. We'll need a lot of development and improvement before we can afford it.
Thank you. One final question from the chat. How Shell contemplates to be zero neutral by 2050 if fossil resources still represent half of the carbon feedstock and energy source for its petrochemicals and plastics in 2050?
That is a very good question. I think that a part of the answer will be in still having CCS to try to bridge the gap for being net zero. CCS is not the final solution, but it might be an assistance in order to get to the net zero before that. But mind you, the chemical industry is a small part of Shell business. The bigger part is really the energy. And I think that we will also make a lot of progress towards net zero for the energy sector. And I'm curious to see how much of the emission will remain to the chemicals by then.
Okay, thank you again, Jean-Paul.
Yep, most welcome, Elizabeth.
Now, our fourth and fifth speaker are Professor André Kodakov from Lille University and Professor Joris Thibaut from Ghent University, who are both partners in the PSYCHE project. André Kodakov graduated from the Moscow State University in 1987, received his PhD degree in 1991 from the Russian Academy of Sciences, and his habilitation degree in 2002 from the University of Lille. Currently, André Kodakov is a CNRS research director and leader of catalysis for energy research group in the UCCS CNRS laboratory in the University of Lille. His research interests cover catalyst and reactor design, aspects of conversion of fossil and renewable feedstocks, reaction mechanisms and kinetics, in situ and operando techniques. His team maintains ongoing collaboration with China, Brazil, Russia, and several European countries. Joris Thibaut graduated from Ghent University in 1998, received his PhD degree at the same university, and went to the Institut de Recherche sur la catalyse in Lyon for a postdoc position in 2003. He was appointed as assistant professor at Ghent University in 2005 and subsequently associate professor at the same institution. Since 2014, Joris is full professor in catalytic reaction engineering at the LCT at Ghent University. Today, he is heading the catalytic reaction engineering research group, comprising about 15 junior researchers. They actively investigate a variety of large-scale industrial reactions and more particularly the rational design of the corresponding catalysts, as well as of the reactors in which these catalysts are employed.
Okay, fine. So thank you for the kind introduction, Elizabeth. And it's indeed our pleasure from André and me to talk a bit on the efforts we have been doing as part of the PSYCHE project in the direction of COX, because we have been looking both at carbon monoxide and carbon dioxide conversion, more specifically to light olefins, for which André has been focusing, André and his team has been focusing on the experimental side, and I, from my side, have been focusing on the computer-aided catalyst design. So, finding an ideal catalyst together with finding the right operating conditions is in fact a bit of search for a needle in a haystack. Sometimes you can be quite lucky and the needle can be quite clear and quite evident to find. But unfortunately, in most cases, it will more feel like the situation on the right-hand side. And well, we're stuck. We do not know what to do, or we can have ideas. And our try or our attempt is to guide those ideas by developing computerized tools and doing modeling in order to support that. And that's exactly what we have been doing as part of the PSYCHE project, tailored towards Fischer-Tropsch synthesis gas, Fischer-Tropsch synthesis. I think Fischer-Tropsch by itself does not need a big and major introduction, and there's a variety of catalysts that can be used that will lead to different product slates, but André will talk a bit more on that. The most important thing I wanted to convey still right now was that for the modeling perspective, from the modeling side, we have been doing a combination on the one hand of developing models based upon elementary steps, so our so-called single event microkinetic model, but we have been making the transition also towards machine learning in order to better grasp what is happening within loads, huge data amounts.
Okay, yeah, you are okay. So thank you for one nice introduction. So, and I would like also to say a few words about the project, which is a nice example of collaboration, because experimental work, which was principally performed in our laboratory in Lille, and modeling and analysis of data, which was performed in the University of Ghent. So first, when we started developing, actually gasification is a very important route for valorization of plastics, which was also discussed in the previous talk. And it's allow actually valorize all the plastic, which we have a mixture of plastic, which may have different chemical composition. So, and in our work, we focus mostly, say, on Fischer-Tropsch synthesis, on conversion of CO and CO2, which are produced by gasification of plastics. So, and the first question was, of course, the choose of active metals for this reaction of active catalyst. And this actually a small table show different transition metals, which can be potentially used for CO2 hydrogenation. And one of the important criteria was first, if you want to produce hydrocarbons, because our goal was produced light olefins, is to choose the metals on which we have carbon monoxide dissociation. Because if you don't have carbon monoxide dissociation, it can be, or it's very hard, we can produce, for example, methanol, which also another product, however, was not in the target of this project. So after considering the chemical properties, so we see that in yellow, you have the metals where you have relatively easy CO hydrogenation, which use there is iron, cobalt, nickel, ruthenium, which can be the most interesting one. And also we have to take into account the cost of these metals. So actually on all some chemical properties, because if you want to produce, say, light olefins, the best will be, of course, from chemical point of view, and from also the cost will be iron. And finally, we choose iron as the active metal for CO2 hydrogenation. Then we also worked with promoters, because iron itself actually can be used for CO2 hydrogenation, but the product distribution can be very broad and sometimes not the desired one which we want. So, and some of these aspects we discussed in the presentation of Professor Kondratenko. So finally, we focus on promoters, because we have to optimize the selectivity towards light olefins. And in our work, we use high throughput experimentation method. So it's actually allows us to test many catalysts at the same time. I will show a little bit on the next slide. So, and we found different types of promoters which can be used. So it's quite a broad range of promoters. Some of them actually were used already by other groups. Some of them new. So, and I just here just briefly classified these promoters in soldering promoters, soldering metals, which are used for soldering. So it's bismuth, lead, antimony, and tin. basic promoters. So it's alkaline earth metals like potassium, cesium, barium, calcium, transition metals which have multiple oxidation state. So it's like molybdenum, chromium, tungsten, cerium, vanadium, manganese, and also other metallic promoters which also can be used for modify the property of the catalyst. So and then actually our strategy, I would say, for searching for the best catalyst for this reaction. Of course, first we choose, as I said, iron-based catalyst. Then we work with promoters, and the promoters, they can affect activity, selectivity, and stability of the catalyst. Then another important parameter is support. So in our case, we use supported catalyst, and we try to find the best support for CO and CO2 hydrogenation. And then, of course, we use combined characterization using different methods. So X-ray absorption spectroscopy, Bauer, XPS, and other techniques. And also, of course, one of them, say, the most important finally is the moment of truth when we test the catalyst in the reaction. So for that, we tested all these catalysts using high throughput approach, using a Avantium Florence reactor with 16 parallel reactors. Also use this reactor, and also use, of course, when we want to optimize experimental condition, we have a set of laboratory scale laboratory reactors which we can use for some specific goals. So then first I will talk about light olefin synthesis from CO. Here just the results of testing of 27 promoters which was tested, and you see that they have different here is conversion, so which represents activity. They have different conversion. So and from that, of course, you can see that some promoters have higher activity. So for example, like bismuth, tin, lead, also antimony, so it's kind of soldering metals. So and these promoters were tested then in greater detail in our work. And especially what we're interested in correlation between light olefin selectivity and conversion. So here are the data. So we see that we found the general trend. So if we want to obtain very high selectivity to light olefins, the reaction should be conducted at very low conversion, and we increase the conversion, we basically lose light olefin selectivity. So there is a general trend which is valid for all promoters. However, some promoters have, I mean, good effect on selectivity, and we found especially bismuth and lead, so which have high selectivity, which in different conversion we obtain higher selectivity to light olefins on bismuth and lead. Then, of course, I don't go in all details of the work which was conducted, because it also was a topic of PhD thesis of our students, and also work of postdocs. So I just say it's just a general conclusion which we found with light olefin synthesis from CO. So what we found for CO hydrogenation to light olefins, we found the best promoters. Basically, it's tin, antimony, bismuth, and also lead. Lead, however, is a toxic metal, so we don't follow in greater detail because we're not supposed to use for some application. So what we found that is interesting, many interesting phenomena which published. So it's for especially that promoters which can diffuse on the surface because they're liquid, quasi-liquid at the reaction conditions. So they form different interaction with iron. So sometimes we can observe by microscopy partial structures from partial structure between iron carbide and maybe promoters. Sometimes for antimony, for example, by X-ray absorption spectroscopy, we observed alloy formation in the catalyst. For some, we can see iron nanoparticles and localization, very close localization of the promoter. So by different techniques which can be used. So we see sometimes the dispersion, we put promoters on the catalyst, and during the reaction, completely the structure completely changes. So this is quite interesting results. Also, we found that these promoters result in increase in turnover frequency. So they have actually multiple effects, and one of the most important effects that these promoters increase the activity of iron, of active sites associated with iron carbide in the reaction. So which is one of the results of this interaction between promoter and iron issues. So now I just give the floor to Joris to follow.
Yeah, thank you, Andre. So indeed, having those data on CO hydrogenation, on Fischer-Tropsch synthesis starting from CO, having that at hand, we used our modeling strategy in order to try and better understand what was happening. So methodologically, we are making use of the single event microkinetics in order to simulate the performance of what is happening. And in there, we make use of a model that is having kinetic and catalyst descriptors. So the starting point of the methodology is situated over here. And that means that in here, we are simulating the behavior and in the first instance at a selected set of operating conditions, we simulate the behavior we generate a library of catalyst descriptors, and based on that library of catalyst descriptors, we generate the corresponding performances in terms of conversions, selectivities to certain products. And these simulations are then matched to the experimentally observed performances in order to determine and see which values of catalyst descriptors correspond to which experimentally observed behavior. And depending on the agreement on how close we get a match between simulated simulation results and the experimental observations, we may have to iterate along this cycle and then generate additional virtual catalysts, which is part of the targeting, as described in Laura's work, which was a PhD prior to the PSYCHE project. But Anoop, the PhD student working on the PSYCHE project, has been making use of that methodology in order to apply it to Fischer-Tropsch synthesis. This slide demonstrates how that has been done. So in the figure, you can see in the upper left, here the blue dots represent all the experimental, all the simulated performances. In a plot where we have conversion and selectivity. But of course, there are various performances that we can look at. Apart from the conversion, we can also look into the selectivity, the methane make, the selectivity to light olefins, and the selectivity to heavier components. So with respect to the performances, we could see that the various catalysts that we had been looking for, the lead promoted one, the bismuth promoted one, and the pure iron catalyst were situated as such over here. And we found for that the matches between the experimental, the overall experimental behavior and the simulated behavior as indicated in these figures. So for the model, well, I will not go in detail in the model, but you see the unique part, the part of the model containing the kinetic descriptors, which is used, or which is supposed to be universal, so which is used to be supposed to be valid for all catalysts. That information is listed in the upper part of the table. The bottom part then refers to the catalyst descriptors that we had to use in order to make the simulations match between the various experimentally observed behaviors. And that allows us to interpret the behavior in terms of well, atomic chemical reaction entropies of hydrogen, of oxygen, and carbon. And that could then make a link further with what Professor Kondratenko has been discussing in terms of reducing or oxidizing behavior of the catalyst. We then further optimized the potential catalyst descriptors, looking for an optimum yield of light olefins. So we looked at optimal conversions and maximizing conversions, maximizing selectivities, resulting in optimal yields, which are situated in this area in a space determined by the atomic chemisorption entropies of oxygen, carbon, and hydrogen. So the optimal performances that could be achieved for the iron, the bismuth, and the lead promoted ones are situated over here. So if we could make those atomic absorption entropies move into that direction, we see that, well, at least according to the simulations, because the challenge is to do it experimentally, there is still some margin possible for improvements. This was work that has been done essentially based on the single event microkinetic way of modeling things. And that relies on a reaction network based upon elementary steps, based upon detailed reactor equations. And we have to face reality that with the amount of data that we are getting exposed to, that it becomes challenging to analyze everything in such kind of detail. So we also started exploring the use of artificial intelligence, machine learning, making more apparent models and making use of an automated treatment of the data. And that is what Anoop has been doing in order to assist the catalyst design within the PSYCHE reaction network. Now, how did we do that, or how did Anoop do that? He has, in the first instance, starting from the single event microkinetic model, which was available for this reaction, he generated training data in order to determine what kind of technique, what kind of machine learning technique would be the most suitable in the case of Fischer-Tropsch synthesis. So here I focus on the light-olefin selectivity, but similar figures, similar analysis has been done for other responses. And we evaluated various kinds of machine learning techniques, going from the more simple ones, essentially based on the linear types of regression, towards the most complex one, the artificial neural network, which is the most complex one that we have considered and which allows to account for non-linearities. Non-linearities which were and are clearly present in the simulations, the single event microkinetic model simulations, and also represented by the experiments. So, and with respect to the light-olefin selectivity, the ideal set of operating conditions situated at higher temperatures and well, not extremely high pressures, but also not too low ones either, that proved to be the ideal range of operating conditions. Now, the downside of machine learning models being that the fundamental insight that you can acquire with elementary step-based models, that is something which is lacking to have it automatically from machine learning models. So that is why there are techniques such as the SHAP value in order to assess that importance. And that allows, for example, to determine the global SHAP value on the one hand and local values on the other hand, clearly indicating the ranking of the input variables, the importance of the input variables, that temperature is the most influential factor to determine the performance in Fischer-Tropsch synthesis, followed by the pressure, the space-time, and the hydrogen to CO ratio. And this can be slightly different for different responses. So there is the conversion on the one hand and the light-olefin selectivity on the other hand. If we want to look more locally, we can also plot those SHAP values as such. So the global aspect is still evident from how wide the values that reported are. The direction of the impact, whether it is a positive or a negative impact, is evident from the color code, as you can see bottom here. So with respect to the conversion, we only see positive effects. With respect to selectivity, we also see an inverse effect over here. So that is how we are using those techniques and how we also intend to apply them later on for the CO2 hydrogenation, from which the experimental work, at least partially, has been done already.
Thank you. So for that, because if we talk about general syngas, especially gasification of plastic, we produce syngas which contains CO. However, it's significant, can contain significant amount of CO2, and also we have to think about, say, valorization, utilization of syngas feedstock rich in CO2. So for that, we, apply similar approach to design of the catalyst for CO2 hydrogenation. And actually, we also tested, the iron phase was chosen as the active phase for this reaction, and we prepare a wide range of the catalysts for CO2 hydrogenation. Actually, what here, after first we started with silica, because silica was chosen as quite interesting support for CO hydrogenation. However, for CO2 hydrogenation was not the best, because on iron catalyst on silica produce significant amount of methane. Finally, we switched to zirconium oxide, which uses as a support for this catalyst, and we prepare large range of the catalysts. So here there are two groups of catalysts. One third group of the catalyst was just prepared by, say, addition of small amount of promoters to iron catalyst. And the second one, we added potassium, because what we found in this work is that alkaline support, especially potassium, was the most, say, maybe efficient one. They significantly affect the catalytic performance of this catalyst. So, and in terms of, first, of course, of activity was important. So the reaction rate, we see that the promotion of the catalyst basically affects the reaction rate, and significant the effect was when we add potassium promoters. Then the second important issue, maybe the most important one, is the selectivity. So, and we also found two groups basically of the catalyst. First, containing potassium or alkaline generally. Here, what potassium was tested, and also tested cesium actually. And the second one was without potassium, so just promoters. So, and you see that if you measure classical dependent selectivity conversion, see two different trends. On potassium-based catalyst, of course, we obtain much higher selectivity to light olefins, and also the selectivity decrease as a function of conversion. So typically, if we talk about the numbers, so for this type of catalyst, if we, the highest selectivity to light olefins we can reach is about 30, maybe 35%, which is basically obtained at, at 20-25% of conversion. So, and then, of course, when we see decrease in the selectivity with conversion, we see what actually forms at high conversion. And also here there are two different cases. I think first case is, with the catalysts which were not contain alkaline metals. So in this case, at higher conversion, basically what we produce significant amount, of paraffins. So, and if we talk the catalyst which is promoted with alkaline metals, at higher conversion, we produce a significant amount of C5+ hydrocarbons. So it's not very heavy hydrocarbons, so typically between C5, C10, so which we produce at higher conversion. So we have different dependent on selectivity, so possibly different same reaction mechanism on the catalyst which contain alkaline metal and non-alkaline metal. So, and then on the basis of these results, we choose the most, say, efficient catalyst for this reaction. And we just, of course, by comparing all the data, because we also conducted extended characterization, try to correlate structure performance. And what we found that which parameters affect actually the selectivity of olefins from CO2. One of the first parameters is iron reducibility, because it's relevant to formation of iron carbide. Here's a nice example of the catalyst promoted with copper. Of course, it's more classical, say, example. However, we produce small amount of copper with significant reduced reducibility carbonization of iron, so it's have good activity on catalytic performance. The other way is of course with basicity. So we found that in fact by one addition of these promoters on the zirconia on the catalyst, so results in different basicity. So and actually the highest basicity may be not the best, but there is kind of correlation between basicity and catalytic performance. And this another parameter is iron dispersion. what we also found by using microscopy and other characterization technique, but the promotion basically in most cases results in better iron dispersion and smaller iron particle size, and so this can be one of the reasons of high reaction rate. So the best promoters what we found for this reaction is alkaline metal, because really when we add small amount of alkaline metals, the activity performance changes a lot. And also in terms of the second promoter, because we can tune further the catalytic performance by adding the second promoter. So in our work, what was found the best was copper, molybdenum, gallium, and cerium, which also allow more or less to tune the selectivity to light olefin. However, the effect on the catalytic performance is slightly much smaller compared to alkaline metals. So another important thing, I think, so for that, we tried at the end compare, because CO and CO2 hydrogenation, because we have extensive amount of data for both reactions. So, and what we found, of course, if we talk about hydrogenation, one is important issue is a sustainable hydrogen, because if you want to produce something from CO, CO2, we have to hydrogen produced by gasification, maybe by other source, if we don't have enough produced from gasification. And then what we found, we try to test the optimized catalyst for CO hydrogenation and CO2 hydrogenation, and the optimized catalyst for CO2 hydrogenation and CO hydrogenation. Actually, we found that the catalysts we optimized for CO hydrogenation, they are not good in CO2 hydrogenation, and so and vice versa. So this actually asks us a question. So in fact, what to do if we have syngas which contain both CO and CO2? Actually, the point also that when we have a small amount of CO2, basically the CO, small amount of CO, the CO2 hydrogenation mostly suppressed, because CO hydrogenation proceeds much easily than CO2 hydrogenation. So, and also in terms of efficiency, in Fischer-Tropsch, classical Fischer-Tropsch from CO, I would say we can obtain much higher selectivity of light olefins when we start with CO2. Basically, it's more efficient reaction. So, actually, it was a discussion with our research team. What we consider that the best, in fact, if we have a lot of CO2 in syngas, we convert it to CO, because and then to produce light olefins from CO hydrogenation by Fischer-Tropsch synthesis, because if we can reach selectivity conversion of CO2 to CO by reverse Water-Gas reaction high to 100%, and then if we go by a classical Fischer-Tropsch synthesis from CO, we can reach selectivity to light olefin 60%. It's the best conditions. However, if we work with from CO2, so we have much typically lower selectivity to light olefins compared to hydrogenation of CO. So this is kind of chemical conclusions of our research work. So I will leave Joris to analyze.
To conclude overall, yes.
Yes.
So indeed, apart from those conclusions on the experimental side, so from the modeling side, we also could conclude that the modeling is providing crucial insight in how reactions performances relate the input and the input conditions and the operating conditions. And of course, there's a balance to be pursued between the effort and the insight, that we cannot construct a single event microkinetic model for any reaction. The time and effort that requires makes it valuable to do that for, well, processes, reactions that will be applied at a large scale, but it's challenging to do so for every single innovative chemical reaction that can be performed. And that is where machine learning comes in as a potentially very promising manner to do the modeling and the model-based interpretation. So as we have shown for the Fischer-Tropsch synthesis case study, we started from a single event microkinetic model that was available and with which we have generated a virtual catalyst library, explicitly searching the area of catalyst descriptors where we were having an enhanced light olefin selectivity. The machine learning models were trained based on the single event microkinetic data. And as I have shown, the nonlinear phenomena in there were important to account for, and that we could essentially do with a artificial neural network. in order to then still interpret what is happening with a machine learning model, we have to make use of interpretation techniques. And of course, the aim is in the longer term to be able to work without a single event microkinetic model for specific cases. So in that respect, we need to be sure that in this case, we would have used sufficient data to train the microkinetic model. So that is the part of ongoing work to determine the number of data points, for example, for the training of machine learning models, to also account for the uncertainty which is there, such that we can start using machine learning also for experimental design, and of course to couple it back towards the experimental catalyst development. So that's it. I think there is some time left for questions, brainstorming.
Thank you, André and Joris. Are there some questions?
Hi, I'd like to ask a question. It's Alice is speaking. In your models, sorry, there's an echo. In your
please go
selection,
ahead.
in your selection criteria, do you discern catalyst potential catalysts based on what the other 40% of selectivity would be? So other components, you know, in terms of how they could affect the process, separation, complexity, capex, opex.
Yeah, so the question came in a bit staggered. But what I understood was that you were asking about the other selectivity than the light olefins and how it would impact the process. Yeah. Indeed, it's something which well was not part of the focus right now, but for sure the single event microkinetic model and the machine learning model, to the extent that it would have been trained to it, is also giving information on the amounts of other products that are produced. So the percentage of methane that the methane make that would be made, or the heavier fraction typically than paraffins. And in a process design or a techno-economical analysis, those are then factors that could be accounted for. So we didn't do it as part of this work, which was focused on the catalyst itself. But the information is provided by the models to be employed when that larger development, larger conceptual development is done.
Okay, sorry, maybe I should rephrase. Do you envision that these type of models would be trained over time to discern catalysts that possibly make a byproduct that you don't want, that makes things more difficult from a process perspective going forward, just for example?
Could you briefly repeat?
So your models, you've trained them to look for, or set them up to look for specific selectivities.
Yes.
In the future, do you envision that they would also look for the selectivity of the components that you're not specifically targeting, and how that would impact the kind of catalyst selection or discovery, for example?
Yeah. Yeah, it's so for sure the single event microkinetic model is comprehensive. That simulates the detailed composition, and there I would say it's a matter of the person doing the further development to take the part and the piece of information coming out of the model, what is most relevant, and determine the optimization criteria. Indeed, now we have looked at it from the perspective, we optimize the light olefin selectivity, and well, and the rest comes as it comes. you could indeed define a profit function, which apart from maximizing the light olefin selectivity, includes some constraints with respect to methane make, for example. If the maximum olefin selectivity would come at the expense of a high methane make, well, you may prefer to go a somewhat lower light olefin selectivity, but with a higher, longer paraffin selectivity, for example. So those are then points to be taken into account, yeah, as part of the process design. But I think then yeah. So the short answer is it is possible. I think the long answer is it will all depend on the evolutions of what becomes important when.
Thank you. There's
Okay,
one
thank you.
question from the audience.
Can you hear me? Yes. Thank you for this presentation. Basically, I have two questions. The first one is, in your model, you used some experimental descriptors for prediction. I would like to know which kind of experimental descriptors do you use? And also, the second question is, at some point you present the KNN algorithm, and you say that it's not possible to have good prediction because it's not possibility to have some nonlinear model. But what is the value of the K in this KNN model? Because if you use a low K value, you can have something which is close to nonlinear model. This is the question. Thank you.
Yeah. Well, maybe to start with the last one on the value of K. So the KNN stands for K nearest neighbors. So and K is then the number of nearest neighbors species that is accounted for. And that has been part of the optimization of which KNN model that was used. So I don't remember exactly what number came out of it. I think it was in the order of 5.
It's quite low, so it's possible to escape from linearity with this kind of value for KNN.
Yes, but all also comes there at the, well, it's also a balance between the number of neighbors you take and the amount of additional information you get out of it. So yeah, that's where the optimal balance brought us. So the KNN methodology was performing well, for sure better than the lasso regression, which was essentially behaving quite linear. But yeah, it's essentially where the optimum brought us. Yeah, and in fact, to give a better supported answer, I think we should also look into more detail on what is exactly behind the methodologies.
Okay, and for the descriptors, what was the descriptor? It was something like temperature, pressure. Which kind of descriptor you used to make your prediction?
The descriptors that we used in the case of the machine learning were the operating conditions. So that was temperature, pressure, space-time, and hydrogen to CO ratio. That were the inlet descriptors there. So the machine learning, and maybe I should have stressed that more, the machine learning was applied towards operating conditions, to optimize operating conditions over a single catalyst.
So basically you have 4 descriptors, something like
yes.
That. Okay.
Yeah.
Thank you. One last question from the chat. Based on your data, would you opt for a direct CO2 conversion pathway or rather a 2-step over RWGS?
Two-step in terms of CO2 calculation?
Yeah, would you opt for a direct CO2 conversion pathway or rather a 2-step
over RWGs.
Yes, yes, I think.
Yeah, that's more.
Yeah, more,
I don't know whether you
yeah,
need to.
yeah, okay. No, this I don't need. I just answer because in this case, if we because here we choose there are different way, of course, for CO2 conversion to light olefins. For this project, we work on Fischer-Tropsch base 1, and in Fischer-Tropsch base 1, I think the best way is what we suggest actually, that the first will be to conduct reverse water gas shift, and then to perform Fischer-Tropsch synthesis using CO hydrogenation. So in two-step process will be, I mean, the best, better, according to the knowledge which we have now.
To end, I would like to thank all the speakers for their interesting presentations and all of you for participating to this workshop. I would like to acknowledge the funding received from the European Regional Development Fund via the Interreg France-Wallonie-Vlaanderen program, together with funding from our local authorities, being the provinces of West and East-Flanders, the Walloon Region, and the Walloon Public Service of Economy, Work and Research. So thank you all, have a nice afternoon, and for the people present in person, we still have lunch. Thank you all.
Thank you.